This one is probably the most difficult one on the sheet. Okay, and the reason for it is, by the way, let me preface this by saying, you will not see something like this on the test. Okay, to alleviate a little bit of stress. This is beyond what we would put on a test. Because of the fact that you have two different bases, it makes the problem a lot more difficult. Okay, so here's what I'm going to do. I'm going to kind of show you what I did in the other classes so that you understand it, where it's coming from, and how you work your way through it. What if I did this? Okay. What if I did that? What would I do? Now what? Now, remember when you're solving, isolate, which the base is already isolated now, change it into log form, and then solve. So by doing that, it helps to make more sense on what you're supposed to do, and then I'll put that back in a second. Let's change that into log form. Log base what? 3 of 5 equal to the exponent, 2x plus 1. Okay, so if that was the problem, there it is. You type log base 3 of 5 into the calculator, and then you solve for x. Now, that's not the problem, so we got to put it back the way it was. In this case, what was it, x plus 1? Is that right? X plus 2? Okay. So we've got x plus 2. Still the same thing. Put it back. X plus 2. But now, what can I do with that x plus 2? Yeah, we've got a property that says anytime you take the log of something that's got an exponent, you can always move the exponent out front. So if I take that out front, now it's still messy, but here's where we start to clean it up and start to make it simpler. Log base 3 of 5, bless you, that we can type into the calculator now. We can get an answer for that, or at least an approximate answer. If you do it, I want to say it's like 1.46. Okay. So this is approximately 1.46. I'll just put that in parentheses just so you know what it is. Which now I can take and distribute into the x plus 2. 1.46x plus, if we double that, we get 2.92. Now can you solve for x? Yeah. Okay. Now we get the x's on the same side, and then we solve from there, yeah.
Could you like divide x plus 2 to the other side and become a fraction?
Yeah, you could. Yeah, another option, I don't know if you heard the question. Another option is, at this point, you could divide the x plus 2 over to the other side and then type that in, and then start working your way through. That's fine as well. Okay. So there's more than one way to get there once you get to this step. Okay. But now at this point, now you go through rearrange, solve for x, and it should get you to the answer. Okay. Like I said, in my opinion on this sheet, this one's probably the hardest one because of the fact that you've got two separate bases. Okay. But like I also told you, something that there's not going to be on your test. You want to have something like that to that extent on the test. Okay? All right, let me open it up to you then. Other questions? Yeah, 17. Top or bottom?
Top.
Okay, let's take a look at 17 on the top then. Okay, so here's number 17 on the top, exponential. And remember when solving exponential, again, I keep coming back to the main idea because at least hopefully it'll help you focus what to do first, what to do second. Main idea in an exponential equation, get the exponential part by itself. Right here. I need to solve for that before I do anything else. That's step number 1. Which means? Divide both sides by 20. I can get that. You could distribute if you wanted to. That works. I'm going to divide by 20 because I think it cleans it up a little bit better. So if we divide by 20, we get, I think it's 25. Okay. Now what?
Move the 100 over.
Yep, move the 100 over. We're solving for the exponential part. So subtract the 100 to the other side. Now, yep, we still don't quite have the base. There's still a -1 sitting out there, which means if I divide or multiply by a -1, it becomes positive. So there was step number 1 right there. Get the base by itself. Now what? Yeah, now we switch forms. Now we go from exponential, we switch it into logarithmic form. Okay? So natural log because it's base e. Natural log of what? The 75 equal to, always equal to the exponent, x over 2. And like I told you before, once you switch forms, usually gets a lot easier at this point. There's only one step left. That you type into the calculator, natural log of 75, and then multiply by 2 to get x, and you're done. Okay? Again, I'm going to keep coming back to get the base by itself. Switch forms, solve. Base, switch forms, solve. Every time with exponential equations. Now, the steps to get there obviously change, but the concept doesn't. The main idea doesn't. Tita, question?
13 and 17 on the bottom.
Okay, let's take a look at those. So let's go to the bottom. Let's go to 13. Now we're looking at log equations. Okay, so here's number 13. And again, I'm going to give you a heads up on kind of something to look for and something to recognize right away. We do have the same base, which is good, because otherwise, if we don't have the same base, we can't really do a lot. Then it goes back to like that other exponential one. It makes it a lot more difficult. So almost always you'll have the same base. But here's the first thing that I noticed. When I look at this problem, the first thing I notice is this. I've got 2 logs on the same side that are being subtracted, which means what can I do with those? Condense them into 1. Yep. Anytime you're adding or subtracting 2 logs, condense those 2 logs into 1. Make it simpler. So let's go through and combine those 2 into log of, since we're subtracting, that means we divide the arguments. So we got x plus 4 over x. Okay. Still equal to the log of x plus 2. And now, here's where the part where you've got 1 log that equals the other, which means if the 2 logs are going to be equal, you can get rid of them. Now you can just focus on the arguments. Okay? You got 1 log equaling another log, so now the arguments have to be equal. You go to x plus 4 over x equal to x plus 2, and now it's back to an algebra problem. Solve for x. At this point, you'd multiply both sides by x to get rid of the fraction. You will get a quadratic. Okay, it's going to be a quadratic equation, which means in order to finish off solving, you're going to have to either factor or quadratic formula. And without actually doing it and looking at the answer on the back, the fact that your answer to this one is 0.562 tells me this is a quadratic equation. This is a quadratic formula problem.
So is there
Extraneous?
Yeah.
Yes. Yep. More than likely, again, without actually doing the problem, more than likely what happens when you do the quadratic formula, well, you're going to get 2 answers. One of the 2 is probably negative, which then if you plugged it back in, can't take the log of a negative, therefore extraneous. Okay? So one answer will work, the other one will not. Okay? So that's at least the idea there. Finish it off with a quadratic formula. One will work, one won't. Okay. And then the other one was 17, Tina? All right, let's take a look at that one. It's kind of similar, at least to start, on this one. All right, so here's what you have. I say it's kind of similar because I noticed the same thing at the beginning. two logs on the same side that are added, which means I can condense those two logs into one. If we condense, we have the log base 4. Since we're adding, that means we have to multiply the arguments. So we're going to end up with x squared minus 2x. And now, kind of the same main idea, like we were talking about exponential. We said isolate the base, switch forms, and then solve. Well, in this case, isolate the log, which it is. This is just the log of something. There's nothing outside of the argument. So we've isolated the log. So switch forms, and then solve. Okay? So if I switch this into exponential form, remember we always start with the base. 4 raised to what power? 6. Log always equals the exponent. Yep. 4 to the 6th comes back around and equals the argument then. X squared minus 2x. And now we solve the resulting equation. 4 to the 6th power, correct me if I'm wrong on this one, but I believe is 4,096. Okay, I only know that because I've done it in the other classes too. So 4,096, which I would then subtract to the other side. And now you're right back to a quadratic equation again, which once again either factor or again based on the answers, this turns out it's another quadratic formula problem. Okay? One answer ends up working, the other one ends up being extraneous. Feeling better, hopefully? Understanding, kind of? Okay? And like I said, if you're still feeling like you're still not understanding, okay, and you might be at that spot, that's a real thing, come on in. I'll sit down with you and we'll try to get you past that point. Okay? Like I said, we've got plenty of time yet. We've still got, 5 days until the test? 4 days until the test? Granted, I know I'm not going to be Saturday and Sunday. Obviously, I'm not there to help you, but you still have an opportunity to kind of work through some stuff and try to figure some things out. So there's still time to get help. Okay? But like I said, come on in during ELT today or tomorrow if you're struggling, and I will sit down with you and help you. Okay? All right. Let me go to the other worksheet that I handed out to you today. The good news is a lot of solving. We're still going to be solving. Okay? But now instead of just solving random problems, we at least have an application that we're going to come up with. Okay? So if you take a look, we're just going to kind of work our way through these types of applications. These problems, all of these type of problems would be second day, next Tuesday. Okay? These are ones where you're going to need a calculator most of the time. So you'll see a couple of application problems next week on Tuesday. You will not see any of these on Monday. Okay? So if we take a look, we're going to take an exponential growth model whose graph passes through those 2 points. So here's the idea. Remember, general equation for exponential equations. Y equals a times b to the x power. That's where we started this chapter. Where a is your initial value, okay, it's your starting value, and b, remember, is your multiplier. That's what makes this exponential, that common multiplier. Okay, so I need numbers for those two in order to come up with an equation. What's a? It's right here. There it is. There's your initial value right there, when x equals 0. Okay, 4,453. So I've got one of them, which means I need to find the other one. Okay, so here you go, Edwards. Just started. So 4453. Now, I gave you a second point, and you actually have done this even back in Algebra 1, not with exponential equations, but you did it in Algebra 1. Why are you given an extra point? What do you almost always do with it? Plug it in. Yeah. Take 7, put it in for x. Take 5,024, plug it in for y. And then the only variable left to solve for will be b. And that's what I'm trying to find. So, 5,024 b to the 7th power. That's always why you're given that extra point. Okay, so you can plug it in to find out whatever's left that's still missing. All right, 2 steps to solve for b. What's number 1? Divide that 4453 out of there. Yep. Get rid of that. And then, I don't want b to the 7th power, I want b. What's the opposite of 7th power? 7th root, which you can do on the calculator, but I'm going to do it an easier way for you. Think back to square roots. Square roots are what as a power? 1/2. Cubed roots are 1/3, so the 7th root would be just the 1/7 power. So take this and raise it to the 1/7 power. Okay? That'll undo the 7th power on the other side. And you should end up with, where did I put my answer key? Approximately 1.017. That's what you should get for B. Okay, 1.017. Which means now I can write the equation because I know A and B. I know my starting point, I know the multiplier. So we've got y equal to 4453 times 1.017. And there's your equation that fits at least those 2 points as an exponential equation. Where we're headed then on kind of the rest of the problems, this one doesn't have much of a context. That's why I started with that one. Here's how you find the exponential equation. Now, when there's a context, you could actually go through and say, all right, let's solve for this. Let's solve for that. Now let's actually answer some questions with that equation. Okay. I can't do that here because there is no context. Okay. Questions on that at all? All right, let's keep going. Let's go to number 2 then. So now we've got a little bit more of a context. We've got exponential growth of a population of 500, and 5 years later it's at 1,000. Predict the population after 100 years. So in order to make that prediction, I want to try to come up with an equation. I'm going to show you 2 ways to do this. One, similar to what we just did, and then I'll show you a second way that actually turns out to be a little bit more accurate. So again, if we think about exponential equations, a times b to the x, what's a? Yep, starting population is 500, and again, you have another point. It's just not as an ordered pair, this time it's in words. 5 years later, you have 1,000. That's your extra point. So, 1,000 equals, starting with 500 times b to the 5th power. And we solve, just like the last one. Solve for b. Divide by 500. Raise it to the 1/5 power, the 5th root. And that should give you the b value. Which we get what? 1.149 is what you should get. Okay. Divide by 500 and then raise to the 1/5 power. So 2 to the 1/5 power. Which means the equation that models this is y equals 500 times 1.149 to the x power. That's the equation that is modeling this situation. And now the question is, what would we predict the population after 100 years? Plug in 100, see what you get. Plug it in. What you should get if you use this equation is a huge number. 538,236,162. So your starting population of 500, 100 years later grew to 538 plus million. Okay? There's exponential growth. Okay? 500 became 538 million. Now, I told you I was going to show you a second way because I want you to understand this other option. It's actually an easier and more accurate way of doing this, which will also help you on some other problems. Y equals 500. Still the same starting point. But if you recognize this problem, what we're doing, didn't the population double 5 years later? We went from 500 to 1,000. Which means we could say our multiplier is 2. Okay, it's doubling. But the problem is it's not doubling every year. So somewhere I have to incorporate the fact that it's doubling every 5 years. In the exponent, that's where we can take care of that. Okay, we can write it as the x over 5 exponent. And here, let me explain what that's meaning. Let me explain that one. So if x is 5, 5 years later, what's the exponent? 1, which means I've then doubled 1 time in 5 years. If x was 10, if 10 years later, your exponent then is 2, which means that now it's doubled twice. If x is 15, 15 years later, it's doubled 3 times, and so on. So this is a different way of doing the same problem, where you can factor in the doubling every 5 years. If it doubled every 7 years, it'd be divided by 7. Okay? That's the idea. And then if you go through and you say, all right, well, 100 years, that means it's doubling 20 times over 100 years. That's what 100 divided by 5 gives you. If you type that in, the answer that you end up with is 524,288,000. Quick question. These are very different answers. There's 14 million difference here. Which one's more accurate? Why that one? This one's rounded. This is, you've got a rounded base. This one, we didn't have to round anything. We used the same information. We just used it in 2 different ways. The other reason why I wanted to show you this 2 different ways, when you're dealing with exponential huge numbers, there's the difference in rounding right there. It's got a huge impact when you're dealing with these large numbers of rounding versus not rounding. If I would have rounded this one to 1.15 rather than 149, it would have made it even worse. It would have made it even less accurate, okay? So the less you can round, the better it is. So just as a heads up on this one. And like I said, you'll see this equation or this type a little bit more in some other problems too. Okay, yeah. Emma?
Would that one be considered wrong?
No, if you did this on a test, I'd still give you credit for it. Like if you did this type of problem on a test and you did it this way, I would look at the method and still give you credit for that. Okay, let's take a look at number 3 here. Going back to some of the money problems. Okay. Now, I will give you a quick heads up on this one. I told the other 2 classes this as well. If you remember back to money problems, there are 2 different types of formulas. I will put those on the board, so you don't have to memorize those. I'm not going to tell you what all the parts mean or when to use which one, but I will at least put the formulas up on the board, so you have them and you can use them when you think you need them. Okay? So if you notice, we got $20,000. Interest rate of 10.5%, compounded continuously. There's the key word. Why? Why is continuously my key word? What does that tell me? That is which formula? PERT. That's the PERT formula. Anytime something's compounded continuously, it's the PERT formula. And if it's not compounded continuously, it's the other one. Okay, which I've got another example later on, and we'll come back to that. So this is P times E raised to the R times T power. There's your PERT formula right there. All right, let's plug in what we know. Investing $20,000, that's P, that's still my initial value. It's my initial amount, my principal. So 20,000 times E. Interest rate, 10.5%. Remember, we got to change that into a decimal, so that is 0.105. And in this case, part A is asking for the amount of time, which means that's what we're going to have to solve for. We're going to leave that as T. If I'm asking you for the amount of time to double, what's A? 40,000. If you're starting with 20 and we're trying to figure out how long it's going to take to double, that means we're going to end with 40,000. There's the setup right there. And once you've got it set up, now you're right back to solving our exponential equations again. This is why we're revisiting things, because when we did these types of problems last week, we couldn't do this because we hadn't solved exponential equations yet. Okay? So you couldn't actually do this last week yet. We hadn't refreshed your memory on this. If I'm going to solve this, what's step 1? Divide. Remember? Get the exponential part by itself. Okay? Divide by 20,000, which means I get 2, which by the way, hopefully makes some sense because we're talking about doubling. That's what that 2 represents. Now what? Change it to log form. Yep. Remember, get the base, isolate, change forms, solve. We've isolated, base is by itself, so now we're going to change into logarithmic form, specifically natural logs, because it's base e. Natural log of what? The 2, yep, equal to the exponent of 0.105t. And as I've said multiple times already, whole lot easier now. Now you're ready for the calculator. Natural log of 2, type it in, and then divide by the 0.105. Divide by that 0.105. The rest of it's a calculator problem. Which, by the way, if you do that one, you should end up with t equaling approximately 6.6 years. So in this scenario, that $20,000 would become $40,000 after a little more than 6.5 years. Quick question, I'm not going to do the second part, but quick question. If I asked you in part B the amount of money you would have after 10 years, what's the only difference? Go back to your equation, you no longer have this 40,000, that goes back to being A, and just plug in 10 for T. Get an answer. And that one's just a straight calculator problem. Just plug it in and see what you get. What you should get, if you do it, is $57,153.02. Okay, 57,153.02. So 10 years from now, that's how much money you would have according to this problem. In for T, yep. Okay, number 4, we've done one like this before. And now hopefully it'll make a little bit more sense as we, because of one of the previous ones we've already done. You've got a radioactive isotope that has a half-life of 1620. And we're trying to find the initial quantity if after 1,000 years you have 1.5 grams left. Okay. So again, this is an exponential equation. Here's the difference. They're saying find the initial quantity, which means what am I solving for? Yeah, I'm going to find A in this problem, which means I must know everything else. I must know what the multiplier is. I must know what X and Y are so that I can then solve for A. In this case, the 1.5 and 1,000, there's your extra point. Okay? 1,000 years later, and the 1.5. Now, as we work our way through this, we know we're ending with 1.5 grams. Okay, that's the ending amount after the 1,000 years. We're trying to find the starting amount. How much did we have 1,000 years ago? What's my multiplier? Please don't overthink this. What is it? Yeah, it's a half-life problem. We're multiplying by, we're always taking a half, and then half of that, and half of that, and half of that. You're constantly multiplying by a half. That's your multiplier. Okay? Half of what you started with, and then half of that again, and half of that again. So your B value is a half. Okay? And now here's one of those, here's why I showed you earlier the second way to do that one problem. Am I taking a half every year? Nope. I'm taking a half every 1,620 years, which means we've got that fractional exponent again. Okay? So you would have you'd have X over 1620, but we know X. It's 1,000. Okay? Which again means this exponent, notice, is less than 1, which means we're not even 1 half-life through this problem. Okay, that's what the exponent is representing. It's not even to 1 yet. We haven't gone 1 half-life yet. Yeah?
So if it was a half-life like every 1 year, would it just be like to the 1,000?
Yeah. If it was every year, if your half-life was a year, then it would just be like to the X power. Then you don't have to worry about the per 1620 or whatever. Yep, that's exactly it. So now, in this case, now we solve for a. This part, you can plug into the calculator and get an answer, and then take 1.5 divided by that answer, and you solve for a. What you should get is approximately, if you do it, 2.301 grams. 2.301. Like I said, type that into the calculator and then take 1.5 and divide it by that answer to get it. Okay. So your starting amount 1,000 years ago was a little bit more than 2.3 grams of whatever radioactive substance you were dealing with. All right, next one. Let's go to the back side. We got two more. This one, again, we're back to one of the money problems. Is this one the PERT formula? Why not? Semi-annually. We are not compounding this continuously, so it's the other formula. Here's the other formula. There's your other money formula that you're working through. And so once again, let's start taking the information that I know, plugging it in, and then we'll solve for what we don't. So notice, the question is, how long will it take you to become a millionaire? How long means we're going to be solving for t. We're trying to find the time. If I want to become a millionaire, that's the ending amount. I need to end up with $1 million. So there's your ending amount. What's the starting amount? It's the $7,500. Yep. You put $7,500 into the bank. You're trying to figure out how many years later should I come back and collect my $1 million. Okay, that's what we're trying to figure out. 1 plus interest rate as a decimal. Be careful on this because that's a simple place to make a mistake. 5% is 0.05, not 0.5. That's 50%. Okay, so 0.05. The n, yep, is the number of times you're compounding every year. So semi-annually means twice a year. Divided by 2. And then we'll have the exponents 2t. So we set up an exponential equation. Okay? Yeah? No. Yeah, I said I'd put them on the board. You have to know which one to use when and what all the stuff is, but I'll put it on the board so you don't have to memorize the formula. All right, so now we're solving again. We're back to solving an exponential equation, which means we need to get the base by itself. So divide out the 7,500. Doesn't come out real nice, so you could leave it as a fraction. Otherwise, it comes out to approximately 133.3 repeating. Okay? You take 1 million and divide it by 7,500. Here's my suggestion, and I mentioned this the other day when we were doing problems 51 and 53 from that book assignment. Those were the really messy ones that we kind of cleaned it all up. Same thing here. That's why I went over those. I knew this was coming, and this is the same type of thing. I'm trying to solve for the base. Well, let's not leave the base looking like that. Let's get an answer. Let's actually get what that equals, which, if you do it, the stuff inside parentheses is 1.025. That's a little bit nicer, at least, rather than 1 plus 0.05 over 2. Raised to the 2t power. And now, once again, just like previously, exponential equation, which means now, go to logarithmic form. Log base. Okay. Once we get the base by itself, we switch to log form. Base of the exponent is the base of the log, 1.025, of, in this case, the 133.3 repeating, or like I said, you could leave it as that fraction. It's a little bit more accurate. There, we talked about rounding. 1 million over 7,500 equals, always equal to the exponent. And now the calculator comes into play again. Type the log in, see what you get, and then divide it by 2. What you should find in this one, if you started in this case, how long is it going to take you to become a millionaire? About 99 years. Okay? 99.08 years is what you end up with. And therefore, your kids or grandkids can enjoy that $1 million for you. Okay? All right, last one. Population of Stevens Point. Back in 1990 was 22,000 people. Population in 2007 it rose to 35,000 people. We're going to try to find an exponential growth model that fits this situation that then I can use to predict the population in 2020. Okay? So, this again is just an exponential equation. A times b to the x. What's A? It's my starting amount. Now that's not what Stevens Point started with, but that's where this problem is starting. That's your first data point. Okay? So, A is 22,000. And again, here's that extra information that you're given. You're given X, you're given Y, so that you can find the multiplier. You've got 35,000 is kind of your ending population, so many years later. And how many years later? 17. Yeah, so B is raised to the 17th power. So, divide out the 22,000, and then what power will you raise that to? Yeah, you want to take the 17th root, which is the 1/17th power. Okay. And if you do that, you should get approximately 1.028 as your multiplier, your B value. So there's your equation. There's the exponential equation that's modeling this Stevens Point problem. And now, let's answer the question. Let's predict in 2020, what do I plug in?
30.
Yeah, 30 years later. Okay, you started in 1990 with your first data point. So 30 years later is what you're trying to predict. And if you do it, you should end up with an answer of approximately 50,375 people. Which, by the way, somebody in one of my other classes looked up, and it's way off. It's like 26,000 is what Stevens Point has right now. It's not even close. Okay. By the way, why would it not be close? Part of it could be rounding. Starting number could or could not be real close. And if you think about it, how many data points am I using? One other point. Not real accurate. When you're trying to model something, you probably should have more than one data point. You probably should go through and put together a few more than that. So here's what I want you to do. Let me hand out the assignment here quick.